morning, class. My name is Samuel. 2230036664. This is group 1. So we are going to teach a lesson about electromagnetic induction. So this is the instructional objective of ours. We are going to be using effective simulations while trying to make this concept understandable. So by the end of this lesson, Elana will be able to explain Faraday's law of electromagnetic induction collectively. So I would like to first start by introducing what an electromagnetic induction is. Then we proceed to the simulation that we are going to be using. So electromagnetic induction is the process by which a current can be induced due to the changing magnetic field. So without further ado, let's jump right into the simulation, and I'm going to give you an overview of how we are going to be using the simulation. Then another group member of ours will take over. Okay, this is what you have. This is the first simulation from University of Colorado, and all I'm going to tell you, it is only letting you know what you have here. So here we have a bulb. This is the simulation. This one is the bulb. This is the coil, and this is the magnet with the two poles, north and south. To start again, you just click here and everything runs. So what we do, we just plug in and out the magnet. The group member, another group member is going to do that. That's all for my part. Thank you.
Good morning once again. Good morning, my name is Junior Bayro. We will be listening now 2230215551. Let us continue about electromagnetic induction experiment as we have electricity use expression. So let me keep explaining how we can change these variables so that our experiment is done. So according to the Faraday, he has explained two ways of making this electromagnetic or induced electromagnetic force or induced current. The first way is to fix the coil and change the magnet. The second way is to fix the magnet and change the coil. That's two ways we can use. First, we are making induced current. From our simulation, let us do it. I can first set the photometer. I can also set the magnetic field lines. But let me remove these lines in order to make it clear. Here can be just. First of all, if I have the fixed magnet and the fixed coil, nothing we have. We don't have any electromotive force or induced current. But if I try to change the magnetic, our magnet, for instance, moving it towards the coil or away the coil, there will be a creation of electromotive force along the loop. If I move it towards the loop, you see on the voltmeter there is a change of direction which shows there is a voltage or a current which is being created. And if I move it away, you see also there is a creation of induced current. So this is how we can do in order to make our induced current. Let us the next colleague, my next colleague, continue explaining other more.
Good morning,
18764. Also, we are going to continue our lesson where we are going to change the loops and where here we are going to change the loops, or we are going to use the loops with different number of times, and we are going also to see the change of that loop. You see here we have two loops. As you see, the number of times of the first loop is different from the number of times of the second loop.
Yes.
And if we plug the magnet inside the first loop, we are going to see the change from the second loop. I hope you are observing what is changing.
Yes.
And let us also use the second loop. Are you seeing the change?
Yes.
What we can conclude here, the number of loops is directly proportional to the AMF which is going to be induced. If the number of loops increases, also the electromagnetic force that will be produced or induced will also increase. And we are going also to change the directions of magnet. If you have observed the way for the first change that we did, you have seen that the arrows or the needle of that voltmeter was starting from that side to was starting from left to right. And if we change the poles of if we swung the poles of magnet, the needles of that voltmeter will start from right to left. So I can stop here, and the member of group is going to continue. So thank you.
Good morning once again. Good morning. My name is Yvonne Anivarere with registration number 22 26 975. Now, I'm going to continue with looking at what you call Faraday's law of induction. As you have seen in the simulation, when the magnetic field is changing with time, it induces what? It induces electromotive force. Simply saying, Faraday's law relates the change of magnetic field with time and to the magnitude of electromotive force that is induced in what? In the loop. By using a formula, Faraday law, Faraday's law. To state that it is here. This is electromotive force. Electromotive force is equal to the change in magnetic flux with time. And together, this is the part of Faraday, which relates the change in magnetic field through the loop with the electromotive force that is induced in the loop. We have another man talking about this. He added something on this Faraday law, who is called Lenz Lenz's law. Lenz's law tells us about the direction of the flow of this electromotive force. Simply, it is the current. The flow of current will oppose or will be in opposite direction to the cause or to the magnetic flux that induces it. He said that the electromotive force will be to go to the negative, the opposition to the change in the magnetic field flux with time. But this is for when you have a single rule. But what if we have any turns to the rule? We will add the number of turns. To have this one will be negative to the n multiplied by change in the magnetic field flux with time. Where this is n means number of turns. Now this one means Rukundo. What is this?
Magnetic flux.
Thank you very much. You clap for him. This is the magnetic flux. Magnetic flux. And what is this? Josue. This is the electromotive force. It is an electromotive force. Motive force. And we know that whenever there is electromotive force, we have a current as you have been seeing it in the simulation. Thank you. Now you can call upon another member to continue with the application of this.
So, good morning.
Good morning, Claudine.
My name is Tishime Claudine with grade number 22302137. So, we have been discussing about the Faraday's law. Now we are going to see how can it be applied in your situation. As you have seen here, from about that, we have seen different materials. Once you are going to use Faraday's law, you can use it for designing simple generator using those materials. First, you can use these stronger magnets. Are you seeing here?
Yes.
With coil and bulb. So once you are going to do it, you can plug these magnets. Can you see?
Yes.
How it can be made? And the bulb is so it is very important because it is used to generate it, to make a simple generator. Another application I can say, Faraday's law can be used in hydroelectric plant. So, thank you.
Hello.
Hi.
Good morning.
Good morning.
Okay. I'm here by the name of Elise Rambana with reg number 22 10 11 20 7. As we have other presenters have presented the more, this is the time we are going to sum up all of what they have presented or have said. I think everyone have followed the way within previous presenters, and now I'm going to assess you. I'm going to ask you what you will stay within your mind after this presentation. Here are some questions I prepared for you, and I would like to ask one by one what the question, and then you will be able to answer if you have followed the way. Well, let's go for the question number one. Which of the following scenario would successfully induce an electromotive force? I'm gonna to ask you this question, and then you will answer by using what you have learned during presentation. In a stationary coil of wire, A. Placing a strong bar magnet inside the coil and keeping it perfectly still. B. Moving a bar magnet quickly toward or away the coil. If you put the magnet quickly away or toward the coil, you will say what should happen. Then C, keeping a magnet near the coil in a vacuum where there is no air resistance. D, increasing the thickness of the wire in the stationary coil while the magnet is far away. And then one of you is gonna raise her hand up and then tell me what is the correct letter corresponding to the correct answer of the question. Yes, you?
For me, I can answer
You can answer?
B.
Then you are going to explain for us why you choose B.
I choose a B because we have studied that electromotive force is produced due to the change of magnetic flux and time. So moving the bar magnet quickly we produce induced electromotive force.
Okay, clap for him. The following question. Why is there a negative sign in the mathematical statement of Faraday's law? You are going to read yourself for this and then you will give the answer. Why is there a negative sign in the mathematical statement of Faraday's law? Sam, you can answer? This is the consequence of Lenz's law. Good. Clap for him also. Okay, I see that you have understood well, so it is the end of our presentation. Thank you very much for your kind attention.